In this video, we'll look at how we can start using the softmax function in PyTorch for performing classification. The essential steps for performing any kind of classification in PyTorch are as follows. First, we need to load our data. Next, we create our model. Next, we train the model on training data. And finally, we view the results by using our model to classify test data. Let's begin by loading our data. We'll import the common modules used before. And further, we'll also include torchvision.transforms and torchvision.datasets. Torchvision.transforms provides us with a lot of useful transformation functions that can be used for computer vision. Torchvision.datasets has many useful pre-built datasets that can be used with our classification models. So here, we must load the MNIST dataset. We have a training dataset and a validation dataset for our input data. We'll use our validation dataset as a test dataset for our classification models. Just a small note, since in previous lectures we have used the terminology of validation set, we'll use the same here to maintain uniformity. So, for our training dataset, we specify the train parameter equal to true while loading the data. We also specify the transform parameter as transforms.toTensor, and by specifying this, all the MNIST images will be loaded as PyTorch tensors. We do the same for the validation dataset. The first element of the train dataset contains a tuple. The first element of the tuple is the actual MNIST image loaded as a tensor, and the second element of the tuple is the actual class of the image, which in this case is 2. Similarly, the second element of the training dataset is also a tuple containing the image and the class of the image. Thus, all elements of the training dataset will be in this form. Now, let's take a closer look at the single tuple of the training dataset. The first element of the tuple is a 28 by 28 float tensor of the image. And the second element contains a long tensor, which is the actual class of the image. In this case, the image is 2, so the second element of the tuple will be a 2. Now let's talk about creating a model for performing classification. We'll use our softmax classifier that we created previously. We'll concatenate our 28 by 28 images to a 1D vector. Our images are 28 by 28 dimensions. Our input dimension will be 28 times 28 to the softmax classifier. Also, since we have 10 output classes, our output dimension will be 10. As learnt previously, the softmax classifier uses parameter vectors for classification. Since we have 10 output classes, we'll have 10 weight parameters and 10 bias parameters for softmax. Each parameter will be 784 dimensions long. Here's a visual representation of one such weight parameter. Let's convert this parameter to an image, and we see that since PyTorch initializes all the parameters randomly, this image just looks like random noise. In the labs, we have provided the plot parameters function for you to visualize the initial values of these parameters, which initially look all like noise. Next, we specify our loss criterion function as cross-entropy loss. In PyTorch, when the loss criteria is specified as cross-entropy loss, PyTorch will automatically perform softmax classification based upon its inbuilt functionality. Another note, the input for the loss criterion here needs to be a long tensor with dimension of n, instead of n by 1, which we had used previously for linear regression. Here we are simply specifying our optimizer and learning rate for our model, just like we did for logistic regression. We also have a few other parameters that we will use to keep track of the number of epochs, the misclassified samples, and the correctly classified samples. So we create our train loader, and our batch size will be 100. Similarly, we define our validation loader, and our batch size will be 5,000. And again, this is technically our dataset. Now, let's train our model. The code for training the model is in the above left half of this slide. As you can see, everything looks identical except for the new method. What this line does is that for each element in the training batch, it converts the rectangle tensors in a batch to a row tensor. Now let's look at one epoch. In a single epoch, we first train the model with a train loader. Let's use the block to represent the part of the code that represents training. Then we test our model with a validation dataset. Let's take a closer look at how our validation samples look. These two lines of code will first produce an output. Then they will calculate the max of the predicted output on the validation data. Let's take a closer look at this line of code. If we look at our predicted class y hat, we'll get the largest element of z, and y test will be our actual classes. What this line of code does is that it compares each element of y hat with the corresponding element of y test. We get a binary vector, which contains 1 at the index if there's a match at the corresponding elements of y hat and y test. Otherwise, it contains a 0 if there isn't a match. We sum all the values in this binary vector. For this toy example, the result will be a 4. We'll convert the result to accuracy and store it. Now let's review the results of classification in the softmax model. So before training, our weights looked like random noise. After training, our weights start looking like our output classes, which in this case are the numbers from 0 to 9. Check out the lab for more information. And that's the softmax function for you. Thank you for watching the video.